In this video, I'll talk through an example of cost-effectiveness analysis from the IWR report that's provided in the readings folder. And it involves protecting this little fella, the veery, which is a small bird in the thrush family. In this example, we have three different types of projects that we can use in order to protect the veery's habitat, and it's our job to figure out what combination of projects would be the most cost-effective in order to achieve any given level of output. We have three different options. The first is planting shrubbery, which provides more vegetation as a food source and an area where the bird can nest. The second option would be more indirect. It's constructing a berm that's going to raise the water table in this area, which is going to increase soil moisture and encourage more vegetation that's naturally there to grow. And consequently, they would have more habitat there as well. And then the third would be to install fencing around the area, which is going to protect the existing vegetation from other predators or other animal species that would eat it and reduce its availability for the veery. Each option has different levels of intensity that we could implement the projects at, and that's going to lead us to different costs and different impacts. For example, if we're planting shrubs, then we could use different densities in terms of the number of shrubs per acre, and that's going to provide more or less cover. If we provide more fencing, then it encloses a larger area, and that's going to scale according to the size of the perimeter. And so ultimately, we have this list of example projects that are provided in the reading. And for each one, we can see how many habitat units. This is just going to be our metric that measures the impact. You can think of this as how many acres of land, or how many nesting pairs of veeries maybe we're able to protect. But anyway, this is what we want to try and maximize with respect to its cost effectiveness, is that we want to maximize the number of habitat units that we can protect at a given cost. So we have the number of habitat units and the cost associated with different intensities of different types of projects. So here for A, these are just planting different numbers of shrubs per acre. For B, we have constructing the berm and raising the water table to different levels, and so on. If we then take all these different potential combinations of projects and plot them on a graph, on the x-axis here we've got the number of habitat units that a particular project provides, and on the y-axis we have the cost in the number of thousands of dollars that it would cost to achieve that amount of output. We can see we've got a lot of different combinations of projects, some of which the squares here are combinations where we're both planting shrubs and also raising the water table. So these projects are not mutually exclusive. What we want to do is try and identify the Pareto frontier that we had mentioned way back at the beginning of the semester when we're thinking about maximizing utility. In this case, we've got a project here that's highlighted, which is inefficient, and we're going to get rid of that. What we mean by inefficient is that there's another project that provides the exact same number of habitat units, but at a cheaper cost. Alternatively, we've got some projects that we call ineffective, meaning that there's another project that provides more habitat units at lower cost, rather. So we're going to get rid of all of those projects that are either inefficient or ineffective. And what we end up with is a set of projects that are kind of on the envelope of this curve, for which there are no other projects that dominate them in the sense of being better or at least as good with respect to both of our metrics, the habitat units and the cost. This gives us our Pareto frontier of efficient projects that we want to consider. We've gotten rid of alternatives that are redundant in some sense. And so now we need to take this set of potential strategies and identify a baseline for comparison. And we're going to do that by trying to maximize cost effectiveness. Our cost effectiveness metric here is the number of habitat units produced per $1,000. In this case, we've got strategy 2 that produces 6 units of habitat for $6,000, an average cost of $1,000 per habitat unit. If we're maximizing cost effectiveness, that means we're minimizing the average cost per habitat unit, because that's just a reciprocal. If we look at a table of the average cost per habitat unit for all of these different efficient strategies, we can see that this second strategy that produces 6 habitat units for 6,000 is the most cost effective. It has an average cost of $1,000 per habitat unit, and every other project has a higher average cost. That means we're going to use it as our baseline for comparison. And similar to what we did with benefit cost analysis, we're going to use an incremental analysis in order to identify what project that represents an incremental investment is most worth pursuing if we're going to go beyond the 6 habitat units provided by strategy 2. So we're going to identify the next strategy that has the lowest incremental average cost per unit of output. What you can see is the next strategy, strategy 3, provides 8 habitat units, and it costs an additional $6,000. It's a cost of $12,000 compared to the $6,000 of strategy 2. Therefore, since we get 2 additional habitat units for $6,000 additional dollars, we have an average incremental cost of $3,000 per habitat unit. However, if we look further down the table at strategy 5, it produces 12 habitat units, which is an additional 6 over strategy 2, and its additional cost is $12,000 more than strategy 2, so it has an average cost of $2,000 per incremental habitat unit. Its average incremental cost per new habitat unit is lower than strategy 3. So that's the one that we're going to pick next and say, if we're going to keep spending more in order to achieve more protection, this is the one that we'll choose. We're going to choose the one that has the lowest average incremental cost. If we keep doing that, going to S5 and then looking at which projects after that have the lowest incremental average cost beyond the habitat units we can get from strategy 5, then ultimately we can eliminate some additional projects from our efficient list and construct this marginal cost curve. What you can see here is that the width of each bar associated with each project tells you the incremental gains in habitat units that you would get from that particular strategy. And the incremental cost is on the y-axis of how much it's going to cost for each of those additional habitat units. So if we look at strategy 5 and refer back to what we had seen before, we knew that strategy 5 goes to 12 habitat units, 6 more than strategy 2, and its incremental average cost was $2,000 per habitat unit for those additional 6 that we could achieve. The marginal cost curve just shows us how that incremental average cost increases in order to obtain additional protection. And this is what we're going to use ultimately to select our preferred alternative. However, we don't have a clear guideline, like a benefit cost ratio being greater than 1, in order to give us a decision rule that says whether or not something is economically justified. Because we haven't converted the habitat units that we can produce to a monetary value, we can't compare it directly to the cost. All we can do is present this type of information to a policymaker, and they can decide how much of the marginal cost is worth it in order to achieve each additional increment. Sometimes we might have a hard constraint. If, for example, the veery was an endangered species, and in order to build a factory nearby or a subdivision for residential homes, we have to, by law, produce a certain amount of protection to compensate for intrusion on their habitat. We would have to replace it, for example, anything that we are losing from the project. So sometimes we have this hard constraint that says we have to produce this amount of impact, but we don't always. And other times we might just look at the curve in this case and say, well, around strategy 10, you can see there's a big jump suddenly. If we want to produce more than 24 habitat units of protection, suddenly the incremental cost goes way up. Decision makers might look at that curve and decide that that's the point where it becomes too expensive. It's not worth going up any further. That's a simple example of how we would conduct a cost-effectiveness analysis in order to identify a preferred alternative for meeting a particular goal. This is an example of a multi-criteria decision-making framework where now we have two different impacts. One, the cost, and another, the number of habitat units of protection that we're providing that cannot easily be monetized. Or there might not be a need to monetize it in the example where we just have to produce a certain number of units of protection. We'll come back to this concept of multi-criteria decision-making in more detail at the end of the semester and bring in more than 2 criteria and talk about how to handle that. But I wanted to show this, even though it's not in the textbook, because it's pretty common. It's something that a lot of projects actually use in order to try and design a system that meets a specific goal that we have. That's it for cost effectiveness. The next videos that we'll show this week are just walking through a more complicated example problem so that you can get lots of practice on problems that look like what you'll see on the homework in the exam. Thanks.